It's a beautiful day in this neighborhood, a beautiful day for a neighbor. Would you be mine? Could you be mine? It's a neighborly day in this beauty wood, a neighborly day for a beauty. Would you be mine? Could you be mine? I have always wanted to have a neighbor just like you. I've always wanted to live in a neighborhood with you. So let's make the most of this beautiful day. Since we're together, might as well say, would you be mine? Could you be mine? Won't you be my neighbor? Won't you please? Won't you please? Please won't you be my neighbor?
Good morning, everybody. Welcome to Tibbetts Physics. What is crappin' in? Today we're going to do Chapter 8 problems, which is on rotational equilibrium and dynamics practice problems. So let's look at number 1. Buddy the elf and a human being are trying to use a revolving door. Elf, on the left, exerts a force of 625 newtons perpendicular to the floor and 1.20 meters away from the hub's center, while the human, being on the right, exerts a force of 850 newtons perpendicular to the door and 0.800 meters from the hub's center. Find the net torque on the revolving door. So let's draw a diagram of what's going on. We'll draw the center right here for the hub. Buddy the elf is 1.2 meters away to the left of the hub. We'll label that R. And he is exerting a force of 625 newtons upwards. Let's call it F sub buddy. F sub B, 625 newtons. The human being is 0.8 meters. Let's call it R2, sorry. R1 for buddy. The human being is 0.8 meters to the right. And that human is exerting a force upwards of 850 newtons. F sub H equals 850 newtons. We're looking at torque that's exerted on the door. So the person on the right, when they're pushing upwards, they would cause the door to rotate counterclockwise. That would give us a positive torque, because counterclockwise is positive. Buddy the elf on the left side is also pushing up on the door, and that would cause it to rotate clockwise, which would give us a negative torque if it travels in that direction. Just like the net force, the net torque is the sum of all the forces. And we have the torque of Buddy the elf on the right, so the torque of Buddy, plus the torque of the human being on the left, or on the right, sorry, and Buddy was on the left. Let's break down the formulas for torque. So the net torque, that's what we're asked to solve for, is the torque of Buddy, which is the force of Buddy, times how far away he is from the center of rotation, plus the force of the human being times how far away they are from the center of rotation, R sub H. And from here, all we have to do is plug and chug. Notice that Buddy the elf is to the left of the center of rotation, so R would be negative 1.20 meters. So the net torque, in this case, will equal 625 newtons times negative 1.20 meters plus 850 newtons times 0.800 meters. Plug and chug in our calculators, we get the net torque to equal negative 70 Newton meters. Number 2, Will applies a force of 300 newtons at an angle of 60 degrees to the door, 2 meters away from well-oiled hinges. So there's not going to be friction between the door and the hinges. Let's draw a picture of this before we get to the question. So here's the hinge of our door. This is the door itself, and we know it's 0.2 meters. Or sorry, 2 meters. And Will is exerting an upward force at an angle. So don't draw this part, but he's pushing on the door at an angle. I'm going to draw it to the right, just to keep the vectors consistent, with a force of 300 newtons. Fw for Will. And the angle that he creates relative to the door is 60 degrees. Because there's an angle, we could break Will's force into its components. The force of Will in the x direction and the force of Will in the y direction. As we can see in this picture, I know the vectors aren't drawn tip to tail, right here, sorry, or tail tip to tip. But as we can see in this picture, the only force that's going to cause the door to rotate is the force of Will in the y direction. So when we calculate the torque of Will, we want to use this force in the y direction. Letter A asks, find the torque on the door using the position of the hinges as an axis of rotation. To find the torque, all that is the force times the distance away from the axis of rotation. In this case, it's the force of Will in the y direction. So I'll put F sub y times the distance away from the axis of rotation. F of y will be F Will sine of theta, because it's opposite the angle. So the torque will be F Will times the sine of theta times R. So now we just plug in chug. 300 newtons times the sine of 60 degrees times 2.00 meters. And we get the torque exerted on the door to equal 520 newtons meters. Letter B. Nick places a wedge on the other side of the door 1.50 meters away from the hinges. So on the other side, let's put a dot right here, we have a wedge 1.5 meters away. Let's call it R2, D2. What minimum force must the wedge exert in order for the door to remain closed, assuming Will pushes with the same force? In other words, if we want the door to remain closed, that means the door can't rotate, which means we want to know what's the minimum force exerted by the wedge when the net torque is 0 Newton meters. So we say the net torque is going to be the torque of Will going upwards and the torque of the hinge or the wedge going downwards. I'm going to say that we have the torque of Will minus, we'll include the negative here because it's going in the opposite direction, the force is, minus the torque of the hinge. And we want the net torque to equal 0. So we say 0 Newton meters is going to equal the torque of Will, which we already calculated to equal 520 Newton meters, minus the torque of the hinge is the force of the hinge times how far away it is from the axis of rotation. And we're solving for f of h. So we'll subtract 520 over and then divide by negative r. That's going to give us, let's see here, negative 520 Newton meters all over negative r equals the force of the hinge. Negative 520 Newton meters divided by the distance away from the point of rotation, 1.50 meters, equals the force of the hinge. Plug and chug, and we get 347 newtons. Sorry, I forgot the negative 1.50. F sub h equals 347 newtons. Next question. Number 3. Sophie of mass m sits on the left end of a seesaw. A plank of length L is 4 meters, pivoted in the middle. Where should Luca of mass capital M sit if the system, the seesaw plus Sophie and Luca, is to be balanced? So let's draw what's going on in this picture. We have a seesaw. Here's our pivot point. We're told that Sophie is on the left side. And we want to figure out where Luca is somewhere on the right side. So let's draw a picture somewhere on the right. And again, in the middle, we have our pivot. So what we want to do first is label the forces that are acting on the plank in the system. We have the force of gravity acting on Sophie. Let's just call it F sub s. The force of Sophie, but that's her force of gravity going downwards. We have the force of gravity due to Luca going downwards. We'll call it F sub L. We have the force of the gravity of the plank going downwards. So the force of gravity of the plank, let's call it F sub P. And then we also have the normal force. So that's the force of the plank pushing up, the force of the pivot, sorry, pushing upwards on the plank. So F sub n. So we have the force of Sophie going down, the force of Luca going down, the force of the plank going down. All those are their force of gravities, and the force of the pivots pushing upwards, which is the normal force. And we're told that Sophie is already on the left side. So the distance between Sophie and the point of rotation is 2 meters. We can call that R sub s. The distance between Luca and the point of rotation is what we're trying to find. R sub L equals question mark. The distance between the pivot and the point of rotation is 0. And then the question is, what about the plank? Well, what we're going to do is use the center of mass of the plank. And the center of mass of the plank is right in the middle, which is at the point of rotation. So let's set up the net torque formula of all the torques acting on the system. Oops, sorry. So the net torque is going to equal to, the only upwards torque is the normal force, and then minus the torque of Sophie, minus the torque of Luca, and minus the torque of the plank. Now let's expand these into the torque formula, which is the force times the distance from the point of rotation. We want this balanced, so the net torque will equal 0 Newton meters. So we have, the normal force times the distance from the point of rotation minus the force of gravity from Sophie and her distance from the point of rotation, minus the force of gravity from Luca and his distance from the point of rotation, and lastly, minus the force of gravity from the Planck and its distance from the point of rotation. As we can see in this formula, the force of gravity from the Planck is, in its distance from the point of rotation, is 0, because it's at the center of mass is at the center, is at the point of rotation. So we can get rid of the force of gravity from the Planck. The normal force from the pivot point is also at the center of rotation, so its R is also 0. That leaves us with just Sophie and Luca. What we're trying to solve for is R, how far away should Luca stand so that the seesaw doesn't rotate. So let's add Sophie to the other side and then divide by the force of Luca. So that's going to give us F sub s, R sub s, all over negative R sub L, the point of rotation of Luca. Oops, sorry. All over negative F sub s, Luca's force of gravity, equals R sub L. That brings us down to R sub L is equal to the mass of Sophie times the acceleration due to gravity, that's her force, times how far away she is from the center, all over the mass of Luca times the acceleration due to gravity. And I've got the negative sign right here, from dividing by negative the force of Luca. R sub L equals negative the mass of Sophie, 55 kilograms, times 9.81 meters per second squared, times, she's 2 meters to the left of the pivot point, so that's going to be negative 2 meters, all over the mass of Luca, 75 kilograms, times 9.81 meters per second squared. And we get Luca stands at a distance of 1.47 meters to the right of the pivots. And that's part A, but part B is a little bit easier, or shorter to answer, I should say. Letter B, find the normal force exerted by the pivot if the Planck has a mass of 12 kilograms. Letter B, we can utilize Newton's second law, which is A equals F net over M. We're going to do this in order to find the normal force exerted by the pivot. So now we're just going to look at the forces acting on the system, similar to what we have on the left for the torques. So we have the normal force upwards minus the force of Sophie minus the force of Luca minus the force of gravity from the Planck. And what we're solving for is the normal force. Oops, all over the mass, sorry. If we multiply both sides over by the mass, that gives us ma. And then what we can do is expand the force formulas for each object. So the normal force is what we're trying to solve for, minus the force of Sophie, that's mg, ms times g. The force of Luca is m Luca times the acceleration due to gravity, minus the force of the Planck, which again is the force due to gravity from the Planck, so mp times g. The object, the Planck, is not moving, so its acceleration is 0, which means ma goes away. To solve for the normal force, we'll add everything to the other side. So that gives us the normal force is equal to ms times g plus ml times g plus mp times g. For the sake of completeness, let's plug and chug. 55 kilograms times 9.81 meters per second squared. We could have taken g out, but too late now, I guess. Plus 75 kilograms, 9.81 meters per second squared. Plus the mass of the plank, 12 kilograms, times 9.81 meters per second squared. Plug and chug, and we get the normal force to equal 1,390 newtons. And that's the force of the pivot pushing upwards on the plank. Next question. Number 4. 3 objects are located in a coordinate system where M1 is 5 kilograms and 0.5 meters to the left of the origin. M2 is 4 kilograms and 1 meter to the right of the origin. And M3 is 2 kilograms is on the origin. Find the center of gravity. So let's draw a coordinate system. We have our x and y axis. M1 is 0.5 meters to the left. Let's call it negative 0.5. M2 is 1 meter to the right. And M3 is on the origin. And what we want to do, let's call this letter A since there's 2 questions. What we want to do is calculate the center of mass of these 3 objects. So let's call this X, or center of gravity, I'm sorry. Let's call this XCG for the center of gravity in the horizontal direction. That's equal to the mass times how far away it is from the origin. So let's say M1x1 plus M2x2 plus M3x3. And that's divided by the sum of the masses. So we'll just say M1 plus M2 plus M3. As we can see, M3 is right on the origin, so its x is 0. So we're going to get rid of M3 on the top. And now we just plug and chug to get the center of gravity. That gives us M1, 5 kilograms. M1, 5 kilograms, times negative 0.500 meters, plus M2, 4 kilograms, times 1.00 meters. And that's all over the sum, so 5 kilograms, plus 4 kilograms, plus 2 kilograms. Plug and chug, that gives us an x center of gravity to equal 0.136 meters. So that's where the mass is, the center of gravity or the center of mass is located, 0.136 meters to the right of the origin. Now we also want to find the center of gravity in the y direction, but as we can see, they're all right on the x-axis. So the y center of gravity is going to equal 0.00 meters. Letter B, or the second question, how does the center of gravity change if M1 is placed 1.00 meters upwards? So our new M1 is up here. Let's put 1.00 meters. And M2 is placed 0.5 meters below the origin. So M2 moved downwards. Oops, sorry. M2, in the y direction, it's negative 0.05 meters. Negative, sorry, it keeps on erasing. 0.500 meters. The x center of gravity, because they did not move horizontally left or right, the x center of gravity stays the same. So x center of gravity is still 0.136 meters. But now we can calculate the y center of gravity. Same formula except in the y direction. So let's say m1y1 plus m2y2 plus m3y3. Just like m3 is on the origin, so its distance away from the origin is 0, so we could get rid of that one. And that's all over m1 plus m2 plus m3. Plug and chug, the y center of gravity is 5.00 kilograms times 1.00 meters plus 4.00 kilograms times negative 0.500 meters. All over 5 kilograms plus 4 kilograms plus 2 kilograms. Plug and chug and we get a y center of gravity to equal 0.273 meters. Next question. Number 5. A uniform horizontal beam 5 meters long and weighing 300 newtons is attached to a wall by a pin connection that allows the beam to rotate. Its far end is supported by a cable that makes an angle 53 degrees with the horizontal. If a person weighing 600 newtons, 1.5 meters from the wall, if a person weighing 600 newtons stands 1.5 meters from the wall, find the magnitude of the tension force T in the cable. We're going to skip the last part of this. Let's draw a picture of what's going on to help us label all the forces and then also the torques. We have a wall and a beam is extended horizontally towards the right that's supported by a pin. And the far end of the beam is supported by a rope, or a cable, sorry. And that's what we want to find, the force and the tension by the cable. And we also have a person standing on this beam 1.5 meters away from the wall. This is not drawn to scale. And the angle between the cable and the beam is 53 degrees. We also know that the point of rotation is at the pivot point on the wall. So, let's look at the forces. We have the force of the plank that the person is standing on. Let's call that the force of the beam. Now the question is, how far away is the beam away from the pivot point? So we're going to assume that this beam is one solid material, which means we're going to locate the force of gravity acting by the beam to be in the center of it. So let's call it F sub B. That's the force of the beam. And we're told that's 300 newtons. We also have the force of gravity by the person. I'm just going to draw longer to separate them. Let's call that Fp for person. And then we have the force of the cable. And since the cable is being supported at an angle, we want to look at the vertical force of the cable. Let's call that F sub y. Now really this should be, if we want to draw it accurately with an angle, it could be more over here on the left side. But for now, for the picture's sake, I'm going to draw it on the right side. So we have F of y going up. We also have the wall, but the wall is at the pivot point, so its torque will be 0. And what we want to do is figure out what is the force in the y direction exerted by the cable, the tension force that prevents the beam from rotating. So let's look at the net torque of the system. And in this case, we have the torque of the cable in the y direction going upwards minus the torque of the person going downwards minus the torque of the beam also going down. We want the net torque of the system to equal 0 to prevent the rotation of the beam. So we have 0 Newton meters is equal to the force of the cable in the y direction times how far away it is. I guess we'll put R sub c for cable. Away it is from the point of rotation, minus the force of the person times how far away they are, minus the force of the beam times how far away it is from the point of rotation. And why don't we expand the force of the cable in the y direction, because that's what we're trying to solve for, the resultant. So we have 0 Newton meters. The force of the cable in the y direction will be the tension force times the sine of theta times how far away it is from the wall minus the force of the person. We're given their weight, so we don't have to break that down into the force of gravity. So minus Fprp. And then minus F sub b, the beam, Rb, the beam. And we want to isolate F sub t, so we'll add the torques on the right to the other side, divide by sine times how far away the cable is from the wall. So that brings us down to F sub t is equal to Fp Rp minus Fb Rb all over Rc sine of theta. That gives us the force of the person. Didn't label it over there, sorry. The force of the person, 600 newtons. Times how far they are away from the wall, which is 1.5 meters to the right. Times the force of gravity from the beam, which we're told is 300 newtons. And again, its distance is how far away the center of gravity is of the beam from the pivot point, which is in the midway point, because it's one uniform material. So that's going to be 2.50 meters. All over how far away the cable is from the wall, so that's 5 meters. Times the sine of 53 degrees. Plug and chug and we get the tension force of the cable to equal 413 newtons. Next question. Maybe. After taking a break from marching band, Jacob decides to put on a baton show during halftime using a baton made up of 4 0.2, 0.3, 0.2, 0.3 kilogram balls fastened to the end of very light rods, meaning we could ignore the mass of the rods. Each rod is 1.0 meters. Find the moment of inertia of the baton about the axis perpendicular to the page and crossing through the point where the rods cross. So let's draw the baton. Should be fairly even, but whatever. And we have mass 1, mass 2, mass 3, and mass 4. Let's alternate the masses, so 0.20 kilograms, 0.3 kilograms, 0.2 kilograms, and 0.3 kilograms. And we know the length of each rod is 1.0 meters long. So that's the entire length of the rod. If we look at the point of rotation, the distance away from the point of rotation for each ball will be 0.5 meters. And we want to find the moment of inertia. The moment of inertia is going to be the sum of all the individual ones. And the formula for this one is mr squared. So that's going to be, let's scroll down and give some space, I equals m1r1 squared plus m2r2 squared plus m3r3 squared plus m4r4 squared. So all we have to do for this one is just plug and chug. I equals 0.2 kilograms times 0.5 meters squared plus 0.3 kilograms, 0.5 meters squared plus 0.2 kilograms times 0.5 meters squared plus, last one, 0.3 kilograms times 0.5 meters squared. Plug and chug and we get our moment of inertia to equal 0.25 kilograms times meters squared. Next question. Number 7. Melissa is loosening up her arm before a softball game and tosses a 0.150 kilogram softball using only the rotation of her forearm. Her forearm has a mass of 1.50 kilograms and the length from her elbow to the ball's center is 0.350 meters. The ball starts from rest and is released with a speed of 30 meters per second in 0.30 seconds. Letter A, find the constant angular acceleration of the ball and arm. So here we have a picture of Melissa's arm. It looks like she's on steroids and also has toes for fingers, but who cares about that? So let's just label our knowns first. We know that the mass of the ball is 0.150 kilograms. We know that her forearm has a mass, let's call it the mass of her arm, is 1.50 kilograms. The length from her elbow to the ball center, we'll call that R, is 0.350 meters. The ball, when she throws it, starts from rest. Its final velocity, when she releases it, is 30 meters per second. And it took her 0.3 seconds to wind up and release. Letter A, again, asks us to calculate the angular acceleration, that's alpha. as we can see in this question, we don't know the angular velocities. So let's calculate the linear acceleration first, knowing vi, vf, and t. Oops. And we could just use a equals delta v over t. So that's for the linear acceleration. So a equals 30 meters per second minus 0 meters per second all over 0.3 seconds. We get a linear acceleration to equal 100 meters per second squared. To get the angular acceleration, we know that the linear acceleration a is equal to alpha times r, which means alpha is equal to a over r. That's 100 meters per second squared, all over 0.350 meters. And that gives us an angular acceleration to equal 286 radians per second squared. Letter B. Calculate the moment of inertia of the system consisting of the forearm and the ball. So letter B, we're calculating I. In this case, we have to include the ball plus Melissa's arm. The moment of inertia of a ball is just mr squared. The moment of inertia of Melissa's arm, we're going to make it a rod, kind of like her bone, and that is 1/3 mr squared. Oops. 1/3 mr squared. So now we just plug in chug. The ball's mass is 0.150 kilograms. Times r, 0.350 meters. Plus 1/3 times the mass of Melissa's forearm times 0.53 meters squared. And we get a moment of inertia of the system to equal 0.0797 kilograms times meters squared. Last question for this problem, find the torque exerted on a system that results in an angular acceleration found above. We also know that torque is equal to the moment of inertia times alpha. So tau equals I alpha. We know I, we know alpha, so we just have to calculate the torque. Torque equals 0.0797 kilograms times meter squared times alpha, 286 radians per second squared, and we get a torque to equal 228 newtons times meters. All right, last question for the day, or whatever day this is. A solid sphere of mass m and radius r starts from rest at a height of 2 meters and rolls down a 30-degree slope. What is the linear speed when it leaves the incline? Assume that the ball rolls without slipping. So if we draw a picture, we have an inclined plane, angle's 30 degrees, the height is 2 meters, and we have a solid sphere sitting on top, rolling down. To analyze this problem, we're going to use conservation of energy, but what we have to include is the rotational kinetic energy, because as the ball is rolling down, it's rotating as well. So let's look at the initial energies that we could potentially have, or possibly have, sorry. There's PE sub G, PE sub S, KE linear, now we'll be a little bit more specific, so KE sub L, and KE rotational. In this case, the object starts at rest and is at a height of 2 meters, so the only energy it has to start with is gravitational potential energy, PE sub G. We could have also added, work to this, but there isn't any work from an outside source. And that equals the final energies, same ones, PE sub G, PE sub S, KE linear, so KE sub L, KE rotational, and Q if there's any internal energy. It's at the bottom of the incline, so there's no gravitational potential. It's not a spring. No energy is transferred due to heat, but it was transferred to rolling kinetic energy and also linear kinetic energy. So for our formula, we have gravitational potential energy initially is equal to KE linear plus KE rotational. Let's expand that formula out. mgh for gravitational potential energy equals 1/2 mv squared for linear kinetic energy plus 1/2 I omega squared for rotational kinetic energy. And what we want to do is solve for v, the linear velocity. We have to look up a couple of things. We have to look up the moment of inertia of a solid sphere, and that is 2/5 mr squared. So we'll plug that in for I. And then also we have a v and an omega, and we want to solve for the linear velocity. So what we could do is convert omega into linear velocity using the formula v equals omega r, which means omega will equal v over r. So let's plug in those variables first. mgh equals 1/2 mv squared plus 1/2 I, which is 2/5 mr squared, times omega squared, and omega is v over r, so times v over r squared. Let's expand that out. mgh equals 1/2 mv squared plus 1/2 times 2/5, that gives us 1/5 times m, and then we have a v squared over an r squared, and as we can see the r's will cancel out, r squared over r squared, so times v squared. And now we don't have any omegas, and we're solving for v, so now we can combine like terms. So now we have mgh, well actually before we do that we have an m, so we could get rid of our m's, and now that gives us gh equals, I guess we'll get a common factor here, or a common denominator, since we're adding them up. So that will be 5 over 10 v squared plus 2 over 10 v squared. 5/10 plus 2/10 gives us 7/10. So gh is going to equal 7/10 v squared. We're solving for v, so we'll multiply by 10 over 7 and then take the square roots. So we get v is equal to the square root of 10 gh all over 7, which gives us the square root of 10 times 9.81 meters per second squared times a height of 2 meters all over 7. We get a velocity of the solid sphere to equal 5.29 meters per second. And that's it for me. Thank you for watching, and I hope you found this useful. And I'll see you next time. See ya!